All right, let's get started. Thank you to everyone who has joined us today. This is Poseidon Systems' second webinar, Limitations of Offline Oil Analysis for Gearbox Health Assessment. This webinar will dive into the following topics. What are the most commonly used offline test methods for wear metal and particle counts? What is the correlation between these offline methods and gearbox health? Why is detecting a gearbox fault so unlikely with offline sampling and analysis? And how does online oil analysis compare? If you do have questions, please use the questions section on your control panel to your right. We will have a Q&A section at the end, and so if you have any questions, just ask throughout. Our webinar speaker today is Alex Pelkey. He is Poseidon Systems Mechanical Engineer. He has had 3 years experience in fluid diagnostics, and he earned his bachelor's in mechanical engineering from Rochester Institute of Technology. I'll hand it over to Alex.
Thanks for the introduction, Madison, and thanks to everyone joining us for this webinar today. So while many attendees might be familiar with Poseidon, I'll just spend a few minutes here providing a company overview for those of you who are not. Poseidon Systems was established about 5 years ago to advance condition-based maintenance practices throughout the development and commercialization of a line of fluid diagnostic sensors. Our product line and capabilities continue to grow over time, and we now offer a range of sensing capabilities, including online wear debris monitoring, online oil condition monitoring, online viscosity sensing, and online water contamination monitoring. We also offer custom monitoring systems that include a suite of all of the sensors. We also have an offline ferrous wear debris monitoring system and custom data portal solutions and data collection systems to meet specific customer needs. Ultimately, our goal is to provide customers with the information they need to keep their equipment running longer, healthier, and more cost efficiently. So a few of our key products are shown here. In terms of metallic debris monitors, which are shown on the left, we offer both online products, which are the focus of this presentation, and offline products. These products are designed to detect the signs of equipment failure and in the earliest stages to reduce downtime and repair costs. Our oil quality monitoring products are designed to provide online monitoring for oils to detect the age and contamination in those oils. We offer sensors for monitoring the electrochemical properties of oil, water contamination, and viscosity monitoring. We also have a line of data logging products and fluid quality monitoring systems, which can be shown at the right there, and are designed to meet specific customer application needs. All right, so what was our motivation to conduct this research and compile this presentation? Well, our primary motivation stemmed from conversations with a few wind turbine operators that claimed that they were using their offline oil analysis as an indication of the health of their gearbox. Sites typically send oil samples to a lab to perform ICP-AES, which detects dissolved metals, and they usually do a optical particle counting, which detects free particulates. These two tests, because they can be seen as related to wear debris, are often misinterpreted as indicators of the actual health of the gearbox. And while these offline analyses provide great information about the health of the lubricant itself, it provides a bad representation of the actual wear occurring in the system. So this is just a quick summary of the two lab analyses we're going to talk about today. The left diagram shows the typical setup for inductively coupled plasma atomic emission spectroscopy, or ICP-AES, which is a method used to detect trace metals in a working fluid. The sample is delivered through a nebulizer tube, is charged and exits with charged ions. The light from this is separated into different wavelengths corresponding to the metals present in that sample. This lab test typically quantifies about 22 different elements, but that can vary depending on the lab. On the right is a typical optical particle counting setup. This essentially uses a photosensor to detect the light scattered as particles pass through the flow path. So both of these tests have some limitations. ICP-AES assumes that the sample is homogeneously mixed and that the trace elements present are dissolved into the sample. Only a very small portion of the sample, roughly 1 milliliter out of generally a 4-ounce sample, is used, and it's passed through the filter in a nozzle, which prevents any particles larger than about 3 microns from passing through. So all these dissolved metals we're talking sub 3 micron. Optical particle counting has its own drawbacks. The size of detectable particles is usually limited to about 100 microns due to the size of the detection head. Because this method relies on light scattering, it can't distinguish between metallic and non-metallic debris. So that means stuff like soot, sand, dirt, and even air bubbles can be counted as particles. Another major drawback is that the data is usually reported as ISO cleanliness codes, which allows for huge variances due to each bin essentially being double the size of the last bin. You can get up to 100% error between a code of, say, 15 and 16. So, with the intention of trying to find out what, if any, correlation offline oil analysis had with gearbox health, we conducted a study using real wind farm data. So our data set consisted of 2 to 3 years worth of offline data analysis reports from 137 GE 1.5 wind turbines. So over the course of about 3 years, we received between 6 and 14 oil reports per turbine, depending on maintenance cycles and things like that. Out of the 137 wind turbines, 18 had failures, which corresponded to 184 samples from oil analysis reports that should show signs of that increased wear due to the failure. That leaves the other 119 as healthy wind turbines, which corresponded to about 1,045 samples. So for this data set, we decided to define a failed turbine as one that required a gearbox replacement and a healthy turbine as one that required no significant gearbox repairs whatsoever. Oil sample reports from failed turbines after their gearboxes were repaired were removed from the data set so as to not skew the faulty gearbox data. So this is a typical confusion matrix. It's used to determine how good a binary classifier is, and allows you to adjust what your alarm levels are of that health indicator to best determine a healthy or faulty system. Essentially, here we can have a health indicator that should correlate to whether or not the true condition of the system is faulty or healthy. Essentially, what we're going to do is look at the areas here highlighted in red, as those are the typical areas that give people headaches. So at the bottom left there, we see the misdetection rate, which is the percentage of faulty turbines that were identified as healthy. Next to that, there's the false alarm rate, which is the percentage of healthy turbines that were identified as faulty. Next is the nuisance rate, which is the percentage of fault indications that are actually healthy. So out of all the turbines that we say this one's faulty based on the data, those are considered that turn out to be healthy. So essentially, if somebody has to climb a tower to inspect for a problem that isn't there. If this percentage is greater than 50%, it's actually, you're better off flipping a coin than actually climbing the turbine to determine whether or not it actually has a fault. So the plots on the right is the same information, it's just displayed as a probability density function. The important thing to note is that there should be 2 distinct and separate unimodal distributions, one representing the parameters of a healthy gearbox and the other representing unhealthy indicating parameters. The overlap between these two is the result of false alarms and misdetections. So we'll start with our data from the ICP-AES analysis on our 137 wind turbines. So these are iron concentration for each of the wind turbines is shown here. Using the lab recommended warning and alarm limits of 50 ppm and 70 ppm respectively, we found that iron concentration data across the site was a poor indicator of gearbox health. The chart on the right shows a vertical bar for each of the 137 wind turbines. The ones that are red indicate a failed turbine, and the ones in blue indicate a healthy turbine. So each bar is the highest reported iron concentration for that particular turbine. At the warning level of 50 ppm, there are a total of 16 false alarms, 13 missed detections, and 17 out of 22 detections were actually healthy. This 77% nuisance rate essentially means that a tech had to go climb a turbine only to find out that it was healthy 77% of the time. The values only got worse at the 70 ppm alarm limit. A 0.8% false alarm seems good because that's a minimization parameter there, but that's only because there was only one detection. And in this case, that one detection happened to be a healthy turbine. So this chart shows the same data fit to a PDF. We grouped the data in sets regarding how much earlier the sample was taken prior to the actual gearbox failure. We would expect to see the peak of the health distribution farthest to the left at the low end of the iron concentration, and each time set of data increasing towards the right as the turbine gets closer to the failure. So as you can see, this is clearly not the case. The overlapping areas here indicate that it would be nearly impossible to set a warning or alarm limit that would correctly differentiate a healthy turbine from a turbine that was about to fail based on the data that we collected for these 137 turbines. So a derivative of iron concentration is the iron generation rate. Because we took these samples over time, it allows us to scale this and see how much concentration of iron was added to the oil given every 100 operating hours. Data from the first 2,000 hours of operation were ignored because that's the break-in period of these wind turbines, and the concentration is often inflated because of the surface wear asperities and internal residue left over from the machining process. So alarm and warning thresholds were simply calculated as 2 and 3 standard deviations from the dataset mean respectively. At the alarm limit, we see a slight improvement in nuisance rate from the original iron concentration values, but it's actually worse at a warning limit. Again, we are seeing high misdetection and nuisance percentages. The false alarm percentages are small, but again, this is only because such a few number of turbines are being indicated as faulty and passing those threshold limits. So data from 6 months before the turbine failure and healthy data was fit to the normalized histogram on the left. This shows how closely faulty and healthy turbines were in terms of iron generation rates. The same data is shown fit to a PDF on the right. We do not see that the mean iron generation rate for the data from 0 to 6 months before the turbine failed is that much different than that of a healthy wind turbine. It is slightly to the right, which would be expected. The mean of that peak is slightly to the right of the healthy, but it's still overlapping to the point where determining a threshold and being able to accurately predict whether or not a wind turbine would fail is nearly impossible. So now we'll move on to the optical particle counting data. So we received particle data in 2 ways. The first way was binned according to the sizes shown at the top there, 4 to 6 micron, 6 to 10 micron, and so on. Using the average particle size for each bin and assuming a spherical particle, we calculated and summed the cumulative volume of particulate matter in each sample. The maximum particulate volume in cubed millimeters from each turbine is shown to the chart on the top right. This data is slightly more useful than the ICP-AES data, but it still falls well short of being a good asset health indicator. For example, if we use a 0.4 cubed millimeter threshold, we still end up with 72% misdetection rate, 50% nuisance rate, and 4.2% false alarm rate. That low false alarm rate is still due to the fact that there's very few turbines that actually meet that threshold. Below the chart at the top there is the data fit to a PDF, which also shows that the probability of a turbine being healthy or faulty at any given total particle volume from these offline tests is almost exactly equal, which can be seen from them essentially overlapping. So the second way the optical particle data was reported is in ISO cleanliness codes. This actually makes the data less clear and defined. The three codes represent the three bin numbers corresponding to the number of particles per milliliter, larger than 4 microns, larger than 6 microns, and larger than 14 microns. The oil analysis lab recommends limits for these three bins as bin 25, bin 14, and bin 11. As you can see on the chart to the right there, not one turbine passed the greater than 4 micron limit of 25. That's the top of that chart, top section of that chart. While the bottom two, every single turbine exceeded the limits for the two larger bin sizes. So it either doesn't see and meet the threshold at all, or it meets it for every turbine we tested. So this clearly adds no value in determining whether or not it's healthy or faulty. So where is this wear debris going? Because it's got to be going somewhere, right? Well, there are a few good answers to that question. The easiest answer is simply the wear is not making it into the sample bottle. The histogram on the left shows the average distribution of particle sizes over the course of a month. By analyzing online data from 100 turbines, we found that a typical turbine, generates 700, 100 to 200 micron particles a month. By taking flow rate into consideration, we calculated out that means there's approximately 100 to 200 micron particle in every 700 ounces of oil. So given a sampling bottle of roughly 4 ounces, that leaves a 0.5% chance that any given 4-ounce sample bottle will contain one 100 to 200 micron particle. So you'd have to take quite a few samples in order to hit those odds. So this kind of leaves the only effective way to monitor this wear debris through online monitoring. Wear debris generation in any system is not a continuous or linear process. There can be huge variations in the amount of wear being generated based on factors like system speed, temperature, oil cleanliness, system vibration, as well as just the general inherent unpredictability of crack and fault propagations. The plot shown here is an example of a real-time ferrous debris concentration in a wind turbine gearbox as detected with our Trident DM4500 wear debris sensor. You can see that a sample taken at point A would likely come up as faulty, while a sample at point B would likely result in a much cleaner sample and likely come back as healthy. This variability makes it impractical to take samples often enough to get a real idea of what the health and wear generation rates of a gearbox are. An online monitor also doesn't become skewed with non-metallic particles such as dirt or dust, and the general trending of this concentration over time would not be affected by stuff like oil changes or filter changes. So now we can get into a single turbine specific example of online versus offline analysis with regards to a fault propagation. So this plot here shows about 2 years worth of data from online ferrous concentration from a wind turbine. The stars on the plot represent each time when an offline oil sample was taken. This turbine ended up needing a gearbox replacement and got one in the middle of 2014 where it's marked with the black arrow. The online wear debris sensor tracked the propagation of this fault and originally identified it as an issue as early as October 2012. The limits for ferrous concentration are actually plotted on this figure. They're just very low on the y-axis in relation to that spike around the beginning of 2014, so you can't really see them. So we'll start with the first offline oil sample taken March 6th, 2013. ICP-AES revealed 5 ppm iron concentration in the oil, which is much below the warning limit of 50 ppm. And the iron generation rate was calculated out to be 0.8 ppm per 100 hours, which is only about 8% of the actual warning limit for that parameter. Particle counting reported an ISO code of 20, 16, 13, which is well within the normal operating range of any turbine gearbox. The two charts on the right show a green horizontal line corresponding to data from the specific turbine in regards to the 137 that were in this data set. The conclusion here would be from this offline oil analysis that this would be healthy oil and a healthy gearbox. So in that same time range 1, we can see the first signs of a fault within 10 days after installing the sensor. Over the course of this time period, the ferrous concentration spiked over the warning and alarm limits over 10 times, with a large spike occurring right at the beginning of 2013. It's also interesting to note here that on March 6, 2013, when the offline oil sample was taken, the real-time concentration from this online sensor showed that the concentration was low, which would make sense given the offline analysis results. So moving to oil sample 2, taken September 12, 2013, the iron concentration and iron rate both increased by about a factor of 2, but they're still both way below the warning limits. Interestingly, the ISO cleanliness codes actually decreased from the first sample to only 19, 15, 12. Again, these values show that there's no real wear being generated, especially not excessive wear, and it's well within the range for a healthy wind turbine. So online oil sampling from that time period shows that the concentration spikes are generally increasing in magnitude, showing that this fault is accelerating and becoming more of a problem, dumping more wear debris into the system. The large spike at the beginning of September is roughly 6 times the magnitude of the alarm limit. So moving on to oil sample 3, this sample was actually taken after the large spike on that original plot. It was taken February 3rd, 2014. It shows the iron and iron rate both increased again, this time by 5 ppm and 0.03 ppm per 100 hours of operation, respectively. The ISO codes reported also increased this time to 22, 18, 14. This iron concentration and iron rate are still both far below the alarm limits, and while the ISO codes increased significantly from the last sample, they're still within the normal operating range that we're seeing from all the other wind turbines in this data set. So at this point in the online data, we see spikes that are dwarfing the warning and alarm limits. The largest spike in concentration here around the beginning of 2014 is about 600 times the alarm level. So at this point, the turbine was derated for inspection and repair. We got to keep in mind here that the offline oil analysis results indicated this gearbox was essentially an average healthy gearbox. So what were the results of the repair? So axial cracks were found on 2 of the rotor side planetary bearings. These cracks had propagated through the raceway and were creating massive amounts of wear debris in the system. These 2 pictures show the faults, and it's pretty obvious that the significant material loss in these cracks is consistent with the readings that our online wear debris monitor was showing throughout the 2-year life of that wind turbine. So in summary, particle counts and iron concentration readings from offline analysis are valuable measurements for assessing oil cleanliness, not gearbox health. The best health management approach combines these 2 methods to get a fuller picture of the system and potential faults that could happen in the future. Online sensors have the ability to provide direct insight into the health of the asset. It gives you the ability to detect and recognize faults in real time. This can lead to smarter maintenance cycle planning, better use of inspections, and minimizing repair costs in the long run. Laboratory analysis is still useful though. Offline samples can provide information about the quality of the oil in the system, how the additive packages are aging, and other potential contaminants besides just wear debris. Understanding the cleanliness of your oil can lead you to maximizing your operating life overall. So by using a combination of these 2 methods, you can better understand the health of your oil, the health of your gearbox, and you can ensure that every maintenance decision is as best understood as possible before sending people out to go climb or change out gearboxes. So that about wraps it up. I would like to thank Art Miller from EDF, who was kind enough to provide us with much of this data that I've shown today. I would also like to thank NYSERDA for their support in helping us field sensors and perform research in the wind industry. I'm going to pass it over to Ryan now for a quick tidbit on how you guys can get involved in our research studies and a preview of next month's webinar. Ryan?
All right. Thanks, Alex. I just wanted to throw out the offer here to others that are attending. We can perform this type of analysis on your data, and we'd actually like to expand this study and go a little deeper with it. So if there are attendees that would like to share with us their historical oil analysis data and have us take a look at it in terms of correlation versus your gearbox failures, here's a few bullets of what we would need. Obviously, the oil analysis data itself, along with a listing of what gearboxes failed, when they failed, and when they were actually replaced, and identification of any oil changes or other maintenance activities that took place on these turbines that may impact the results of our processing. Ultimately, we'll go through and slice and dice the data in as many different ways as we feel necessary to either identify a correlation or prove that there isn't one, and share those results back with you. Our next webinar is going to be roughly a month from now, on June 24th. It's going to be an introduction to Poseidon Live. Poseidon Live is a web-based data portal that we use for gathering, storing, and analyzing sensor data from our wear debris sensors and other sensors. A lot of nice tools have been built into this, allowing you to really pinpoint where problem areas are quickly and sort through all of your data and identify which of your assets need attention. So Amanda will be presenting this webinar, and I hope you all can join. All right. So with that, we'll switch over to some questions. So of the questions we have here, I'll just go down through. First question was, are there any offline analysis methods that you would recommend for determining gearbox health? That's usually the first question we get after this presentation is, well, if these methods don't work, what does? And the foolproof method is online wear debris monitoring, as we presented here. The information that we are capturing through an online wear debris analysis is also present in a filter, and if you are actually able to perform filter analyses on a regular basis, you may be able to get good correlation. The problem is filter analyses are pretty expensive, in the range of $200 to $1,000 per filter, and at least in the wind industry, they're pretty difficult to perform on a regular basis, since you're hopefully only climbing turbines once every 6 months. Let's see, second question. Other than wear debris monitoring, are there other online sensors or sensing mechanisms that you'd recommend for use in gearbox applications? In terms of other online sensing technologies, so we offer several. We have oil condition sensing, viscosity sensing, moisture in oil, and others. Gearbox oils, generally, their oil condition changes very slowly, and you can capture that change through offline analysis fairly effectively by tracking oxidation and viscosity changes, as well as some other parameters. A moisture in oil sensor, water contamination sensor, would be useful in some environments, and with some types of oils that have problems with moisture absorption. That would probably be my primary recommendation. Can the lack of correlation be attributed to improper sampling methods? Again, that's a pretty common question. The sampling methods used, good, bad, or otherwise, aren't going to catch the data that you want to see. The amount of, or the particles that you need to see to determine where just aren't effectively measured in an offline analysis, and aren't even effectively captured in an offline sample, regardless of how or when that sample is taken, due to the almost chaotic nature of a fault progression and wear. But the sampling methods used in the study, we were assured, were done according to industry standard practices. So I don't think that's a significant concern. And let's see, a couple more questions coming in now. Get this to open. So the question on the availability of the presentation. The presentation will be available for download after the fact. We'll be posting a recording shortly. It'll be up within the week. You can go to our website, go to the video archive section, and you'll be able to pull it down from there. The other question, what is the suggested sampling frequency for offline oil analysis? That's really depends on industry. I've seen samples done on a multiple times per day basis, and I've seen samples done as far out as once every 6 months. The wind industry is the longest of any industry I've been involved in. but for a couple of good reasons. It's expensive to go climb that turbine and pull an oil sample, number one, and number two, that oil degrades pretty slowly, so it's not a significant concern. But in other applications, engine applications, certainly far more frequent offline analysis is prudent. When you have a drain interval that's measured in a couple hundred hours in some application, you're going to want to get 2 or 3 samples within those few hundred hours. Good question here. Do you have any data or information regarding the relationship between oil contamination and asset health? For example, the failure of the asset occurred when the oil is contaminated too much. This is actually a great question and an area that we'd like to push the research into. We were focusing primarily on the items that our customers were telling us they were using for assessing gearbox health, the iron concentrations and particle counts. We were not looking for cause and effect type analysis. Did a high particle count eventually lead to a failure, or well, I guess we were looking at that. Did say elevated moisture contamination lead to a eventual failure? I'm sure we'll find some correlations there, and we would like to work with you to perform that type of analysis. All right, with that wraps up our questions. And I believe that is the end of the presentation. It is.